The general conviction among most examiners is that the speculation of how things came to be remains the significant explanation for the early times of the universe. This hypothesis encompasses the formation of stars, planets, and subsequently, life on those planets, including ourselves. Despite its peculiar name, the Big Bang offers an enlightening assessment of what might have occurred. At first, the universe was incredibly dense, compressed into a space smaller than a pinhead, with particles densely packed. From this moment, a massive explosion of matter and energy occurred, known as the Big Bang. This event, happening billions of years ago, initiated the expansion of the universe. In scientific knowledge, it has triggered evolving curiosities about the assumptions of this theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever, experts anticipated that its findings would confirm the theory of the universe's origin. Unfortunately, after just 1 year in space, the telescope stunned experts with its ability to peer so deeply into the universe's past. The James Webb Telescope's extraordinary capabilities revealed countless galaxies dating back to a time so ancient that it challenges our understanding of the universe's beginnings. This discovery has ignited a serious reassessment of what existed before the Big Bang. One pivotal moment in this mission occurred when cosmologist Rohan Natu, working with data from the telescope, unexpectedly discovered a galaxy for merely a brief period after the Big Bang, making it the most distant galaxy ever seen. Natu's discovery sent shockwaves through established experts, highlighting the remarkable abilities of the James Webb Telescope. Its ambitious goal to transform our perspective on the universe has only just begun, promising to unveil incredible insights into the earliest stages of the universe's existence. This era, barely studied until now, holds the key to understanding the formation of the first stars and galaxies. The telescope's discoveries have challenged fundamental theories, revealing systems with properties surpassing previous assumptions. This unprecedented surge of early galaxies has sparked intense scientific inquiry, pushing experts to reconcile these revelations with existing theories. As researchers uncover these findings, they face fundamental questions about the very nature of the universe and the forces that shaped its evolution. Beyond its scientific merits, the James Webb Telescope is stationed 1.5 million kilometers from Earth, shielded from cosmic interference and cooled near absolute zero by its tennis court-sized sun shield. The telescope features a massive mirror and exceptionally sensitive instruments designed to uncover details of the early universe, previously hidden. This period, known as the Cosmic Dawn, occurred around 200 to 300 million years after the Big Bang, marking the moment when the first stars and galaxies began to form. The processes behind this remain a subject of active research, with theories ranging from the effects of dark matter and dark energy to the interactions between star-forming gas and dust. The telescope's observations of galaxies from the cosmic dawn present a unique opportunity for cosmologists to test their interpretations of these complex components. By studying these ancient systems, researchers can either confirm the validity of current models or expose gaps in understanding that could lead to major new discoveries. Initially, the telescope was expected to observe only a few faint and small galaxies in its pilot studies. However, reality has far exceeded these expectations. The telescope's early images of the distant universe revealed a wealth of galaxies with ages, sizes, and brightness levels that defied all predictions. This astonishing influx of early galaxies has sparked a race among astronomers to establish new records for the earliest known massive systems, with new revelations emerging constantly, leaving traditional experts in awe. Following the James Webb Telescope's discoveries, subject specialists and observers have rushed to study the existence of these surprisingly advanced early systems. Some speculated that errors in the telescope's interpretation of massive observations could account for these startling discoveries. That said, the consensus remains that these findings represent a paradigm shift in how we understand the early universe. They offer thrilling glimpses into the potential for vast progress in cosmology. The new revelations from the James Webb Space Telescope about galaxies have raised significant questions about the nature of the universe and tested the assumptions of standard cosmological models. While some experts are exploring whether these insights can be reconciled with existing theories, others suggest that they might be the first indications that the universe is far more complex and mysterious than previously imagined. The critical question at hand is our fundamental understanding of how the universe we know emerged from primordial chaos. The early discoveries of the James Webb Space Telescope could reshape our core ideas about cosmic history, providing insights not only into distant galaxies and ancient structures but also into the very nature of our own Milky Way. As Mark McCaffrian, Senior Advisor for Science and Exploration at the European Space Agency, puts it, "You build these machines not to confirm theory, but to break it. You have no idea how it will break." The origins of the James Webb Space Telescope can be traced back to the Space Telescope Science Institute, STSCI, in 1985, even before the Hubble Space Telescope was launched. At that time, Garth Illingworth, then director of STSCI, was tasked with developing a concept for a next-generation telescope. The vision was to create an observatory capable of peering farther into space and time than any instrument before it. Over decades, this concept evolved into what we now know as the James Webb Space Telescope, JWST. The telescope's design was revolutionary. Unlike the Hubble, which observes primarily in visible and ultraviolet light, the JWST was built to detect infrared light, allowing it to look through dense clouds of gas and dust to observe the earliest stages of star and galaxy formation. Its massive 6.5-meter gold-coated mirror and advanced instruments make it the most sensitive telescope ever built, capable of detecting the faintest signals from billions of light-years away. The development process, however, was far from smooth. Years of delays, technical setbacks, and budget overruns led to doubts about whether the telescope would ever be completed. Initial estimates projected a launch in the early 2000s, but the timeline stretched to December 25, 2021, when the telescope was finally launched aboard an Ariane 5 rocket from French Guiana. Once in space, the JWST underwent a complex deployment process that included unfolding its mirror and sunshield, an intricate procedure requiring thousands of steps, each of which had to succeed for the mission to proceed. The tension was palpable among scientists and engineers, as even a minor failure could have doomed the mission. Remarkably, the deployment went flawlessly, and the telescope began its journey to its operational position at the second Lagrange point, L2, a stable location in space where it can remain in alignment with Earth and the Sun. Since its commissioning, the telescope has delivered a stream of groundbreaking discoveries. From identifying exoplanets with atmospheres that may harbor signs of life to mapping the chemical composition of distant galaxies, the JWST has expanded our understanding of the universe in ways scientists could only dream of a few years ago. One of the telescope's most significant contributions has been its ability to study the cosmic dawn, the period when the first stars and galaxies emerged. By observing the faint infrared light from this era, the JWST has provided unprecedented insights into how the universe evolved after the Big Bang. It has revealed galaxies that formed far earlier and grew much larger than models had predicted, challenging long-held assumptions about the processes governing cosmic evolution. In addition to its role in exploring the distant universe, the JWST has also focused on studying nearby phenomena, such as the atmospheres of exoplanets in our galaxy. By analyzing the light passing through these atmospheres, the telescope can detect the presence of molecules like water vapor, methane, and carbon dioxide, key indicators of potential habitability. These observations have reignited the search for extraterrestrial life, providing valuable clues about where we might find it. The implications of the James Webb Space Telescope's findings extend beyond astronomy. By challenging existing theories and sparking new questions, the telescope is driving innovation in fields ranging from physics to computer science. Its discoveries are reshaping our understanding of the cosmos and humanity's place within it, reminding us of the boundless potential of scientific exploration. As the telescope continues to operate, scientists anticipate even more transformative discoveries. From uncovering the mysteries of dark matter and dark energy to pinpointing the origins of life, the James Webb Space Telescope promises to remain at the forefront of space exploration for decades to come. Its legacy will undoubtedly inspire future generations to look to the stars and ask the most profound questions about our existence. Imagining what could come after Hubble, Weir and a small group began laying the foundation for what would ultimately become the James Webb Space Telescope. Unlike Hubble, which primarily captures visible light, the JWST was designed to observe in the infrared range, allowing it to peer much further into the universe. This capability is crucial for studying distant galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its massive, cold, star-like mirror, the JWST became the premier instrument for uncovering the mysteries of the cosmic dawn. The need for the JWST was highlighted in 1995 when the Hubble Deep Field Observation revealed countless galaxies in what was once thought to be an empty patch of sky. This discovery demonstrated the richness of the early universe and underscored the necessity for a telescope capable of probing much deeper into galactic history. Following 20 grueling years of development and a cost of around $10 billion, the JWST was finally launched on December 25, 2021. By July 2022, it was ready to begin its most critical year of scientific observations. Early initiatives, such as the Early Release Science Program and the General Observing Program, were specifically designed to search for early galaxies. While initial expectations were modest, the results far exceeded them. JWST observations have tested existing models of the early universe, revealing galaxies that challenge traditional cosmological assumptions. These groundbreaking discoveries highlight the importance of pushing the boundaries of scientific inquiry and showcase the exceptional capabilities of cutting-edge advancements like the James Webb Space Telescope. As scientists continue to analyze JWST data, they may uncover further insights that challenge and expand our understanding of the universe. When the first data began arriving from the JWST, astronomers eagerly anticipated the results. Many had been preparing their data analysis pipelines for this moment for years. Instead of following the traditional peer review process, which typically takes months, researchers chose to share their findings on preprint servers like AR14, a platform for research papers not yet peer-reviewed. This approach enabled a new form of peer review to occur through online platforms like Twitter, where established experts could quickly discuss findings. Rohan Naidu described this process as science by press release, and the ensuing storm of discussion was both intense and unprecedented. However, concerns arose about the potential drawbacks of this rapid dissemination of results. Claus Pontoppidan, a JWST project scientist at the Space Telescope Science Institute, STSCI, cautioned that while quick sharing facilitated rapid dissemination and discussion, there was also the risk of overwhelming the process. The general consensus among most experts is that the theory of how the universe came to be remains the primary explanation for its early stages. This theory encompasses the development of stars, planets, and life on those planets, including ourselves. Despite its peculiar name, the Big Bang Theory offers a compelling explanation for what might have occurred at the universe's beginnings. The universe was densely packed into a space smaller than a pinhead, filled with tightly packed particles. From this state, an immense eruption of matter and energy occurred, known as the Big Bang, setting the stage for cosmic history. However, advances in scientific knowledge have led to emerging inconsistencies with some assumptions of the Big Bang Theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever built, experts anticipated that its observations would support the theory of the universe's origins. Surprisingly, after only a year in space, the telescope astonished experts with its ability to peer deeply into the universe's past. The James Webb Space Telescope's extraordinary capabilities have revealed galaxies dating back to such ancient times that they challenge our understanding of the universe's origins. This discovery has sparked serious re-evaluation of what might have existed before the Big Bang.